Right, seems like it's time. Welcome back. So I left you with this cliffhanger of this machine right there crashing. So what happens if a machine crashes? It's not a problem at all because the data, as we saw, is stored on HDFS anyway. So that we just need to reassign here the red and the purple regions to another region server. So maybe to her and maybe to him and so on and so on, right? So you just reassign the regions. Okay, so crashing is just not a problem at all. I haven't told you yet the details of how we store it in HDFS. This will come in due time, but basically the HMaster takes care of redirecting the responsibilities. Okay. Any questions on the HMaster? No questions? Then I'll move over to the region servers. So, I'm going to say a few words now on how these partitions are going to be stored on HDFS on the physical layer. These partitions actually have a name. We can call them stores, right? It's just in that case a synonym for partition. So a partition is a store. We saw that this is done horizontally and vertically, right? So no surprise here. We saw that a region is a horizontal slice. So here we have two regions, and each one of the regions has 3 stores, right? And each region is going to be handled by a region server. So the 3 stores that are on the top will be handled by some machine, and the 3 stores that are at the bottom will be handled by some other machine, right? Of course, in practice, there's going to be thousands of regions, right? But on my slides, I cannot fit thousands of them. So I just display a handful number for pedagogical reasons. All right. So now I'm going to zoom in on a store, on a specific store. I'm just zooming in here. So I have a specific partition means it's a region with my minimal inclusive and maximum exclusive intervals. And I have a specific column family, the yellow one, the red one, the purple one, whatever, okay? So I'm looking at one store. So I have my rows within that region, and I have my columns within that column family. And the intersection of a specific row ID and a specific column is called a cell, right? So again, we have, I summarize, the entire table. Then we have the regions, horizontal partitions. Within the regions, we have the partitions, also called stores, and within the store, we have cells, right? Each cell corresponds to one row ID and one column. Who is following? Okay, this is going to accelerate. This is why I'm really taking it slow to make sure that you understand this. Now is the beginning of the complex part, so follow me. Each partition, each store, is the same thing, is going to be persisted to HDFS. I use the word persisted. What does persist mean? To persist means to store some data in a durable way. You store it in the long term. You don't want to lose it. So this is what persisted means. If it's in the memory of the computer, this is not persisted, because if you shut down the machine, this is gone, right? So it cannot be just a working memory. Persisted means it has to be stored at least on hard drives. But we saw that since hard drives crash, what persisted means in the scale of a cluster is on HDFS, right? With the duplicates and so on and so on. All right. So what it means is the content of this specific partition is going to be stored as one or more files on HDFS, and there is a name for these files. We call them the H files, H for Hadoop, right? Because HBase is part of Hadoop. So we call them H files. Maybe it's 1, maybe it's 2, maybe it's 3, maybe it's 4. It can be multiple files for the same partition, right? I will give you the details of that shortly. So each partition is persisted on HDFS as one or more files called H files, right? Now, I'm continuing to zoom in inside these files, because now what I store as files is the entire partition, right? But in a partition, there are cells. So how do I map these cells to the H files? Well, let's assume one H file for the moment before looking at several H files. Let's assume just one H file. So I'm going to take a specific case where in the partition or the store I'm considering, I have 3 rows and 2 columns, right? So this is what I have here. So 3 rows and 2 columns give me 6 cells. And the way I'm going to be physically as zeros and ones, storing these cells in my H file is by enumerating them one by one, right? Because remember that when you store something as a file on disk, what is it? It's a sequence of zeros and ones. It's linear, right? It's an ordered sequence of zeros and ones. As opposed to my logical layer, which has something 2-dimensional, right? So I need to map this 2-dimensional table to a 1-dimensional sequence of zeros and ones on disk. How do I do that? I just go from left, let me get it right, from top to bottom and then left to right, right? So I'm going to do A1, then A2, then B1, then B2, then C1, then C2, right? It's like when you play chess, right? So every time I have a row and a column, and I'm just enumerating my cells, top to bottom, left to right. So first this one, then 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 this one. All right, tack, 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 top to bottom, left to right. I'm just putting them one after the other. And what I'm going to have in this H file for every cell, I'm first going to have the row ID, the column family, and the name of the column here. And here I'm going to have the value. That takes care of A1. Then I have A2. So that's, again, my row ID, my column family, my column name, and then the contents of the cell. Then the third one, B1. So again, I put B1 in there. Then the value. Then again, B2. So I put the row ID, the column family, the column name here, and I store the value, and then the black one, and then the green one, and so on. So you see that here it was 2-dimensional, but I flatten it to a sequence that is 1-dimensional, red, then blue, then purple, then yellow, then black, then green. And for each cell, first the row ID, column family, column name, and the value. In fact, this is a key value model. Again, a key value model, right? Where the key is my row ID plus column family, column name, and the value is the content of the cell, right? So you see the key value model is everywhere. Who is following? Okay, so here is how we mapped a logical 2-dimensional partition to a sequence of cells, right? Now, I'm adding, you know, on top more and more and more knowledge. The next thing you need to know is that HBase, which is very powerful, supports versioning. It means that it also remembers when you erase values or overwrite or add new values, it will remember the past. So what that means is that inside these H files, you don't have just the latest version, you also have possibly past versions. So in that case, you might have the same cell that was A1 here. I changed the color for some reason, but that was A1. And we have here 4 versions. Maybe version 1 was 1 month ago, version 2 1 week ago, version 3 yesterday, and version 4 today, right? So I have these versions. And the latest one, they are stored in decreasing order. So I start with the latest one and then go back in the past, and they are stored together, right? So basically, if I want to be even more precise here, I had only 1 version of each cell. I will, in that case, have all versions of A1, starting with the latest one, then all versions of A2, starting with the latest one, then all versions of B1, and so on, and so on, and so on, right? So it means that in this key value model here, it's not only the row ID, the column family, the column name, it's also a version. So there's 4 parts to my key, all right? Why do we have versioning? This is a little bit of a parenthesis I'm making here. Why do we like to have versioning in databases? Well, you might know that in databases, you might have several people accessing the same database concurrently at the same time. Whenever that happens, it's a bit risky because what they do to the database can interfere, right? So the versions are one of the ways. There's others, but if you version the system with version 1, version 2, version 3, version 4, you kind of avoid these conflicts, because then you have a very clear order on who does which and in what order. It's the same thing. Who's been already using, let's say, Git or SVN, or so some of you, right? In Git, you also have this concept of versions, right? With these fancy lists of letters and digits that you just copy paste all over the place, right? So these are versions. Here it's the same idea, right? We just use integers in the case of HBase. How do we achieve this? That we keep a version even when 100 people are writing to the table at the same time. We achieve this with what's called a lock. Another name for that computer scientists call it is mutual exclusion. Mutual exclusion means you don't want to have 2 persons at the same time writing to the same place. So you need a lock that if somebody wants to write to somewhere, they first acquire a lock, and that locks out anybody else for writing to the same place. Then you write, you go ahead, and at the end, you release your lock, and then somebody else can take over. The way this is done in HBase is per row, meaning that whenever somebody writes to a row, they lock the row for the time that they need to write to that row. Nobody else can at the same time, and then they release the lock for the row. Per row means that 2 people might be working on different rows at the same time. So maybe Alice is writing to row 1, and at the same time, Bob is writing to row 2. That's absolutely possible because the locks are for each row, right? What cannot happen, however, is that both Alice and Bob write at the same time to row 1, right? The system is going to make sure to lock everybody else out from the same row that you're writing to. And having versions is one way of enforcing that, right? So you just sequentially maintain the order. It's first Alice, version 2, then Bob, version 3, and so on. So it goes along with that. All right, so parentheses closed about my versions. Oh, the sun is greeting us again. Nice. So this is spring definitely, and summertime too. Okay, so now I showed you this list of cells. Now we have A1. Oh, I think, I don't know why I put A1, C2. That's probably a copy pasting. I will fix that. Should be A1, N2, B1, B2, C1, C2 in here. But anyway, I have this list of my cells, and I need to map them to a physical file. So what's going to happen is that the red part, A1, is going to be mapped to a sequence of zeros and ones. This is what we call a key value as a shorthand. So I'm going to map the key and the value on disk, then green, then purple, then black, then purple, then blue, and then yellow, and so on, right? So here I'm just redrawing the whole thing. Instead of listing them vertically, I list them horizontally. It's just a sequence of bits written to disk. So now I'll zoom in. Again, I keep zooming in, right? I zoom from the table to the region to the cell, and now I keep zooming in and in and in and in. So let's zoom in again on a key value. What do I have here? Oh, this is interesting. So we have the key, that would be the row ID, the column family, the column name, and the version. We have the value, that's the content of the cell. And now I added key length and value length is there. What is that? So key length is the length of the red zone, the key, and value length is the length of the green zone, the number of bits. Why? Well, I'm opening another parenthesis. I'm going to tell you about prefix codes. But maybe I'll start with a real world example because that's going to be easier. Who has ever been using a landline phone? Most of you, because in the mobile phone, it's no longer the case, right? On a mobile phone, when you call a number, you dial the number, and then you press a button, and then it just magically connects, right? But on a landline phone, what actually happens is that you hear, you pick it up, then you hear this so the tone that tells you that you can dial. It was carefully selected probably a century ago in order to not surprise people and know that they expected to dial. And then you start dialing. So maybe you start dialing, I don't know, let's dial ETH. So 0, nothing happens. 4, 4, 6, 3, 2, 1, nothing happens. 1, 1, still nothing happens. One starts ringing. How did it know that when you press that last one, it was supposed to actually start dialing? Why not before? This is because the phone numbers are a prefix code. There's a magic way in the design of phone numbers that you know exactly when to dial. So now you can think, okay, yes, they all have 10 digits, right? Yes, but it wasn't always the case. In Zurich, now it's 044, but it used to be 01. And that's not so far away in the past. Maybe 20 years ago, it was 01 for Zurich. So the numbers in Zurich, they only had 9 digits, not 10. And yet the whole thing was working. If you dial a number in another country, it's not going to be 10 digits, right? You have 00, then the indicator of the country. That might be just a single digit for the United States, just 1, for Switzerland, 41, and so on, 49 for Germany, and so on. So even that is a variable number of digits. So how come that with a different number of digits possible in every phone number, the whole system just works and knows exactly when your phone number stops? This is called a prefix code. So now I'm doing the same thing, not with phone numbers, but with zeros and ones, but we need the same thing here. Why? Because my phone numbers here are my key values. I need to know where my key value stops. Is everything okay? Okay. So here, this is an example. I'm not going to tell you why it actually works, because that's part of other lectures, but there are ways to make sure when you store numbers like that, when to stop. I picked a simple case. How do I know when to stop? I look for ones and then the first 0 that comes. And I saw 1 bit to 1. So then I know that I stop here and I just read a 0 and I always have a 1 in front, so 1, 0. Then I see, I continue. So this stops here. I read 3 bits here. This is an encoding, right? So I stop here. Right? So then I look again, that's the next phone number, 1, 2, 3, 4, 5, 6, 7, 9 ones, and then comes a 0. So now I know there are 9 ones in here, which tells me that I'm going to read 9 bits in here and then stop. So let's see, 1, 2, 3, 4, 5, 6, 7, 9, and I'm stopping here. There you go. And that's the number I'm reading. So I take all the bits that I read here and I add a 1 in front. That's the next number. Then I read how many ones? 2. So 1, 1, 0, then I read 2 bits. I stop here, right? And then I get the 0, 1 comes from here. I always want 1 to the left. Then 1, 2, 3. So I read 3 bits and I stop here, right? You don't need to remember that. It's only an example. That's actually called the gamma code. You don't need to remember the details. The only thing I want you to see here is that even though I started with just a flat sequence of zeros and one with absolutely no idea what stops when and how to read these different components, since I encoded this in a certain way, I have hints about when to stop every time. It's like magic, right? So there are ways. Again, you don't need to remember how exactly this is done here. But what I want to say, now if I'm coming back here, what I want to say is, if I just store the key values like this, one after the other, I have absolutely no idea when the key values start and stop. I have no idea when to put the where to put the boundary and how to read them. No idea. So I cheat. And what do I do in order to cheat? What I do is I put here the length of the key, always on 32 bits. 32 bits, that basically gives me an integer between 1 and 4 billion, right, to do the power of 32. This is exactly 32 bits. So I read 32 zeros and ones, 32 bits, right? And that's the key length. So I cheated because now I know the key length. Next, also on 32 bits, so 1 to 4 billion, that's a fixed number of bits here. I know that I read the next 32 zeros and ones, and that gives you the value length. I cheated again. I know now the length. How do I now know how many bits to read from here? Well, I know from there, because since I know now the key length, I read exactly the key length in here. Maybe it's 10, maybe it's 1,000, maybe it's 4,321, right? And I read that many bits and I stop. Then how many bits do I read here? Well, I cheated. I stored it there, right? So now I know the value length. So I read exactly the number of bits that the value length told me, and I stop. And since I stop there, I know exactly when the next key value is going to start. This is magic. This is the same magic as phone numbers that know exactly when to dial. For whom is that clear? All right. So again, I repeat, because it's really simple. I cheat by storing the actual length of the key and the value, which is the number of bits that I'm supposed to read here. I cheat by doing that. This is always stored on 32 bits, so I know exactly how to read them. And once I have read the key length and the value length, I know exactly how long this is and how long this is, and I will stop at exactly the same place. Who understands that if I did not store the key length and the value length, I would be completely lost. I would have absolutely no idea how to read the key and the value. Who gets that? All right. So feel free to look at it again offline and to understand, but basically, all I'm doing is I'm cheating by storing the key and the value length before the key and the value, and then I know exactly how many bits I'm supposed to read. Okay, so that I already shown you. Okay, now I'm zooming in again. So we went from the region to the cell to the versions and so on to the key values. And now what I'm zooming in is in the key. I'm within the key now, right? So again, just to show you where we were. I'm zooming in here. This is what I'm zooming in on, the key. And if I zoom in on the key, I get this. This is the entire key. Normally, there should be no surprise here because these are stuff I already told you. What is there in a key? There is the row ID, there is the column family, there is the column name, and there is the version. That's exactly what you see here, right? You see, there's the row ID in red, the column family in yellow, the column qualifier in purple, the timestamp, that's the version, right? And then I'm going to tell you what the rest is, right? But normally, these four here, that's things I've already told you, right? So if I have a row ID, a column family, a column name, and a version, I uniquely identify the cell, the value. Let me start with the gray ones, row length, column family length. This is also the way I cheat. I cheat by putting the length, because the row key might have a different length, right? So I cheat by storing on 32 bits the length of the row, and then I know how many bits to read for the red zone. Then I cheat again by storing the length of the column family name, and then I have the column family, so I know exactly how many bits to read. And then the column qualifier, oh, I didn't store any length for the column qualifier. And yet that's also a variable number of bits. How come I didn't do that? Does anybody see why? I could have put the column qualifier length so that I also cheat and know how many to read. Why did I not do that? Why do I not need to know? Meaning I can deduct it from other places. Anybody can guess? I'm going to tell you otherwise. Maybe in the room, on Zoom, can anybody guess?
Timestamp and key type have fixed length.
Yes, that's exactly the right direction. And as a consequence, can you continue your reasoning? That's exactly the right reasoning. Just continue. So timestamp and the key type indeed have fixed length. You can guess, yes?
You can guess the column qualifier length.
Yes, you can guess. How do you guess it? Yes, over there. Somebody in the room. Oh, almost one hop.
You have the key length, and then you just have to subtract the length of the key type and the length of the timestamp.
Exactly, exactly. That's the trick. I have the key length. Where do I have it from? I have it from there, remember, here. So here I have the key length, you see, on the left. So I know how many bits there are in the key. So it means that now I'm fast forwarding again. Look carefully. I know the total length. That's my key length. So that I know how long it is. This is 32 bits. This I know from here. This is 32 bits. This I know how long it is from here. This I don't know. This is always the same fixed length, and this is always the same fixed length. So I just do a subtraction. The key length minus the 32, minus the row length, minus 32, minus the column family length, minus, I don't know if it's 34, 32 or 64, one of these, and then the key type, which is probably just 1 byte. And if I subtract, then I got, just by calculation, by subtraction, then I know exactly how long that is. For who is it clear? Right? So I could have stored it, of course, but it would have been redundant, right? So if we can optimize things a little bit by saving some space, then we do that. All right, so the timestamp is just an integer. It's a fancy name for integer. And then I need to tell you about the last one. The last one is a marker of deletion, right? If somebody deletes the contents of a cell, it's not actually deleting it, it's marking it as deleted. Right. So logically, it's deleted, but physically, it's still keeping the older versions, but it's also adding this marker that is being deleted. All right. This is just the same slide as before for the version, so I don't need to tell you that to you again. Okay, who is following? Okay, so you see we've zoomed in from the region to the store, to the cell, to the key values, to within a key, the identifiers, the row ID, column family, column name, and version. And so now I'm going to zoom back out. So we've now managed to store the contents of a partition in a file, in an H file, as a sequence of cells, more precisely of cell versions, that is just a sequence of zeros and ones. Now, I need a way that I can read it back efficiently. Because if I just blindly put these zeros and ones and maybe, I don't know, a gigabyte or maybe the size of an HDFS block, that would be 128. Actually, you can easily go more than that. So let's say gigabytes. How am I able to quickly read a specific cell from that file if that file is a gigabyte long? Do I have to read the entire file? In fact, not, because there's a little trick in order to accelerate things a little bit. And the trick is that when we store the data in an H file, we don't just store the zeros and ones, we add a bit of structure to it. And the way we add structure is by storing data in zones. And each zone is going to be roughly 46 kilobytes, but it can be longer if I have more data, because I told you the cells can be very large, right? So if you have large cells, then the zones will just be bigger. But basically, by default, the zone is going to be 64 kilobytes or longer. And in fact, when I'm going to be reading the data, I'm going to be reading in zones. Right. So what that means is that I add to these key values. On the right, you would have just the key values stored on disk. I add what's called an index. So what that index is telling me is that the green zone starts with key 1, the yellow zone starts with key 5, the orange zone starts with key 11, and the gray zone starts with key 17. So now I can directly jump to where I want to read. So for example, this is in memory. I load that part into memory. Imagine somebody looks for key 14. Do they need to read the entire H file? No. Look at the index. Where is 14? Well, it's somewhere between 11 and 17, right? So it's in the orange zone. So I don't need to read the green, the yellow, and the gray zone, right? I can directly jump to here and find my key 14, right? So I saved myself some disk input output, right? I only need to look in that zone right here, right? I know that 14 is somewhere here. I don't even need to read this, and I don't need to read that. Who understands that? It's an acceleration. I accelerate things with this additional index. So in an H file, I don't only have my list of key values, I also have in my H file this high-level view on the keys when the zone starts. Then I can directly jump to where I want to read. Okay. Let's recapitulate things. These things you already know. I just want to make sure the structure, I've already repeated that 10 times, so let's repeat it an 11th one. So we have the level of the table, the entire table, right? Of course, there can be multiple tables in HBase, but we are just looking at one. So this is the level of the table. Then we have the regions. These are my horizontal slices, right? With a minimum and maximum exclusive row ID. Then I have my stores. That's just the fancy name for partitions. So this is then vertical, right? One store for each column family within a region. Then I have within a store one or more H files, right? We looked at the case of one H file, but there can be more, and I'll explain to you how there can be more. There can be more. Within an H file, I have my blocks. What are my blocks? This is what I showed you here, right? These are my zones, right? Here I have 4 blocks. Okay. And then I have the key values, which are the individual cell values for a specific version of a given row ID and column family and column name, right? So again, a table is made of several regions, which are made of several stores, which are persisted as several H files, which contain several H blocks, which contain several key values. That's it. That's the physical level. A word of warning, super, super, super important. These blocks here have absolutely nothing to do with HDFS blocks, absolutely nothing. This is just a detail of the way that HBase writes the files. HDFS doesn't even know about it. The HDFS blocks, for here, they are still 128 megabytes. That hasn't changed. But HBase doesn't care. To HBase, it's just a storage detail of HDFS. So this is the reason why I call them H blocks. That's not an official terminology, H block. They just call them blocks. But I knew that if I call them blocks, then there's going to be confusion with HDFS blocks. So that's the reason I call them H blocks for the HBase blocks. Okay. So far, so good. But we have a problem. Does anybody see the problem? How do I use HBase? There is get, there is put, there is scan, and there is delete. So let's imagine that somebody puts a row in HBase. They do put. Right in the middle of the table, in the middle of a region, somebody inserts a row. Do you see now the problem? Because this row, where will it go? Somewhere in the middle of that, right? Somewhere in the middle of that file. What is this file? It's a file stored on HDFS. So technically, what do I want to do? I want to insert a few bits, my new row, in the middle of a file stored on HDFS. Does anybody see the problem now? On Zoom? Technically, inserting bits in the middle of a file, that's called random access, right? You just randomly add bits in the middle of a file. Does HDFS support random access? It doesn't, right? Remember, when we covered HDFS, I told you the only thing you can do in HDFS is you can create a new file. You can maybe append to the end of a file, but you can certainly not modify a file in the middle. That just doesn't work. So now we have a big problem because we are basically designing a system, HBase. We want users to be able to insert rows in the middle of the tables, but at the same time, we want to store these tables as files that look like this, as a sequence of keys. They must be ordered, my keys, so it has to be in the middle of the file. And the problem I have is HDFS is not able to actually modify a file just like that in the middle. Who understands the problem? Okay. So we cannot do it in that way. We just cannot modify the H file directly on HDFS by adding the new rows that the user of the system is modifying. So we need to be clever. We need to find a trick that is going to kind of circumvent this whole thing and make HBase work in the way we want. So again, within an H file, all my key values are sorted by key, right? So this is A1, then A2, then B1, then B2, and so on. So this is always sorted. So all I can do is append. If I write an H file, I have to write them in the order of the keys and then close the file. So how do we insert new values? That's the problem we have. We still have 10 minutes, so you're lucky I don't have to make it a cliffhanger. I can already tell you now how this mystery has actually been solved by the brilliant HBase engineers. This is how we write new cells into HBase in a way that is compatible with HDFS. Okay. Again, that's a reminder of what we have on disk. That's the same thing I showed you earlier. So let's look at what we have on this. We have H files. These H files, they are made of these 64 kilobyte H blocks that themselves contain key values. So I visually present it to you like this. However, the trick is that the fresh cells, the ones that have just recently been created by the users, I'm just not going to put them in HDFS just yet. I'm keeping them in memory, right? So this is on the top, that's a RAM, something you have in the computer, and at the bottom, that's the disk. So the disk is the persistent layer that you keep even if the electricity, you cut down the electricity. But the memory is only for as long as you have electricity. So the recent cells that I've just been creating are in the memory, but not yet in HDFS. So I don't need to modify any HDFS files right now, right? It's just in memory. Now, if I start with everything stored on HDFS in a single H file, what's going to happen when I add new cells is that I'm actually adding them in the memory, in the working memory, the RAM of the machine, right? So here I just have new cells and or these key values. And what's going to happen at some point is that the memory will become full, right? At some point, I might have added so many and so many of these new cells and key values that my memory is just full. I cannot add anything anymore. So what am I going to do now? I'm going to take all of these key values that are accumulated in memory in all of these updates. I'm going to sort them by increasing key. And I'm going to do something that's called flushing. I flush all of these key values to disk. And again, I sorted them in memory. Since they are sorted, all I need to do is write them to HDFS as a file, to the H file, in increasing order. The first one, the second one, I just do it by increasing order of key value. And now I have written an H file in the right order, right, with all of my new key values, right? And that solves the problem because I never had to modify any H file in place, right? I never had to do that. I just accumulate the new values in memory. And when the memory is full, I flush them. I sort and I flush, right? In fact, to be even more precise, I'm not going to wait for the last minute to sort the key values. I could have, right? I could just put them in memory. And then when I need to flush, then I take the time to sort. But in fact, there is a way to maintain some data structure in memory that keeps it sorted, right? So these are tree structures. I'm not going into the details of that, but this is something that is taught in data structures and algorithms for the computer science curriculum. So there is a way that I can keep my data sorted at all times in memory for a quite moderate cost, right? And so basically, when I want to flush them, I use the structure in memory to output them in a sorted order. And that's it. For whom is that clear? For whom is it not clear? Who is following? Okay, you are following. I'm just making sure step by step, right? That I do not inundate you if you're lost. Okay. So again, the trick is we don't immediately modify the H file. We just accumulate in memory. And then in a single flush, we write all of the key values that had accumulated so far. But I have a problem. I mean, I still have a problem. Now it's another problem. The problem I have is that this is in memory. And as I told you, if it's in the memory and the electricity is cut, then I lose everything. So now I have a problem because if something happens to my machine or it crashes or whatever, I'm just losing not the bottom. So this here I keep the H file that's on HDFS, but everything in the memory that's called the mem store, this is lost if I have no electricity anymore, if there is a crash. So I need to solve that problem. And there is also a solution, as you can imagine, for that. And that is a generic solution. It's not just for HBase. Actually, many, many big data systems have that. And the solution is called a Writeahead log, WAL. So the secret of a Writeahead log is that at the time that somebody wants to write a new cell, before it gets into the memory, I have a barrier there, like the customs that say, no, not so fast. Do not just put the cell in memory just yet. We first want to keep a record, a journal, if you want, a journal of all the updates that come to the memory store. So before it gets stored in the mem store, I add it to a log that is called an HLog that keeps track of all my changes. In the HLog, I don't sort my key values by key. I just keep appending in the order of arrival. So this is on HDFS, but HDFS has no problem with appending, right? Because since I just add my key values as they arrive, they are always written at the end of the HLog, always at the end. So I just append in the HLog. That is no problem at all in HDFS. I can absolutely append the data as it arrives. But again, this is not sorted by key here. This is sorted by order of arrival. So that's not an H file. That's why it's called an HLog and not an H file. This is called a Writeahead log. Every region server has a Writeahead log for the entire machine. If there is no problem and the computer doesn't crash, the Writeahead log is totally useless. But if the machine crashes, then we are happy that we had it. Right? Because if the machine crashes and we lose the content of the mem store, we just reopen the HLog and replay the whole journal of writes. You can compare if you want, because we've already seen that kind of thing somewhere before. Do you remember in HDFS how we preserve the data on the name node? There is this snapshot containing the metadata, and then this edit log. Who remembers this edit log? The edit log was keeping track of all the changes made to the file metadata in order of arrival, just in case the computer crashes. And if it crashes, we just replay the edit log. This is the same thing. This here is exactly the same thing as the edit log. Right? So this is called a Writeahead log, and this is how I make sure that even if my computer crashes, I will not lose the data because I lose the memory, but it's all in the HLog. I will just need of course, it's not going to be instant, right? If I need to reconstruct, I will need some time to replay the HLog, but at least I have the data and it's not lost. And once I have written to the HLog, then I'm allowed to add it to the mem store, right? And then it gets flushed when the memory is full, right? I'm going to stop here. So just want to check the speed. I really was careful. I know that this is every year. I know that this one is tricky. So this is why I was careful with the speed. But let me check. I do expect that it's going to be less good numbers than in other weeks, but I just want to feel the pace. That's also to make you feel less alone. So if you have the feeling you didn't get everything, then at least you know you're not the only one. And that means that first you can ask all the questions you want on the course element chat or in the Moodle. You can send us emails. Next week, you can ask questions again, and I will again go into the rest of the details, right? But what I want to say is do not be worried if you felt that this lecture was a bit more complicated. That's totally normal. Okay. So thank you very much. Enjoy the exercise session, and I will see you next week again for the continuation of HBase. Thank you very much.